March 1941. A conference room in Washington, D.C. Admiral Ben Moreell, Chief of the Bureau of Yards and Docks, stares at a map covered in red pins. Each pin represents a naval base that needs to be built. Iceland, Newfoundland, Bermuda, the Philippines. Over 100 installations that don't exist yet. The Admiral knows something the public doesn't. War is coming, perhaps within months, and the United States Navy faces a problem that has nothing to do with battleships or aircraft carriers. They need buildings, thousands of them, and they need them impossibly fast. Here's the mathematics that keeps military planners awake at night. A standard military barracks, built using traditional methods, requires approximately 60 days from groundbreaking to occupancy. You need skilled carpenters who can read architectural drawings and cut precise joints. You need masons who can lay brick in perfect courses. You need electricians, plumbers, foundation crews who must wait weeks for concrete to cure properly. Every structure demands shipping tons of lumber, bricks, pipes, wiring, roofing materials across thousands of miles. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Then you need level ground, which often doesn't exist where the Navy needs bases. You need favorable weather, which you can't control. And you need time, which you don't have. The Navy calculates they'll need facilities to support roughly 16 million servicemen by 1943. If every building takes 2 months to construct, America could lose the war before the first wave of bases becomes operational. Traditional construction simply cannot scale at the speed required. It's too slow, too resource-intensive, too dependent on craftsmen who are themselves being drafted into combat roles. But the crisis runs deeper than speed alone. Consider the logistics of building in remote locations. The Pacific Theater presents islands like Guadalcanal, Okinawa, distant Aleutian outposts, where lumber simply doesn't exist. You cannot harvest local materials. Every 2x4, every sheet of plywood, every box of nails must arrive by cargo ship. A single wooden barracks might require 15 tons of materials. Multiply that by thousands of buildings across hundreds of islands, and you're looking at a logistical catastrophe that would consume shipping capacity desperately needed for tanks, ammunition, food, and fuel. The Army tries accelerating traditional methods. They simplify designs, pre-cut lumber at stateside mills, send larger construction battalions. Nothing works. The bottleneck isn't just time. It's the fundamental nature of stick-built construction. You cannot train an 18-year-old farm boy to become a competent framing carpenter in a week. You cannot eliminate the 100 small decisions a foreman makes when walls don't align perfectly or when lumber arrives warped. You cannot solve the problem that wooden buildings require sequential steps that cannot be parallelized. First the foundation, then the framing, then the roof, then the interior, each stage dependent on the previous stage being completed correctly. Meanwhile, soldiers sleep in canvas tents that offer zero protection from artillery shrapnel. Medical supplies rot in tropical humidity because there's nowhere dry to store them. Aircraft mechanics work on million-dollar bombers in open air, where monsoon rains turn engine maintenance into a muddy disaster. Ammunition sits exposed on beaches. The construction gap is costing lives, morale, and combat effectiveness every single day that passes. By early 1941, months before Pearl Harbor, the Navy's Bureau of Yards and Docks knows they need something radically different. Not a better barracks design, not a faster construction method. They need to throw out the entire concept of building and replace it with something closer to manufacturing. They need structures that can be assembled, not constructed. The difference between those two words would reshape how America fights. The war. The British had already figured out part of the solution, or so it seemed at first glance. During World War I, a Canadian-British engineer named Peter Norman Nissen designed a revolutionary shelter that resembled a giant steel barrel sliced lengthwise. The Nissen hut used curved corrugated iron sheets bolted to a simple frame, creating a self-supporting arch that required no interior columns or complex roof trusses. By 1917, these structures were appearing across French battlefields, offering soldiers weatherproof housing that could be erected in a fraction of the time traditional buildings required. The design was genuinely brilliant in its geometric simplicity. The arch shape meant the structure supported itself through physics rather than heavy framing. Snow and rain slid off the curved surface naturally. The corrugated steel panels were strong enough to withstand shrapnel from distant artillery. A crew of 6 men could assemble a Nissen hut in approximately 4 to 6 hours once they understood the system. The British manufactured over 100,000 of them during World War I, and the design remained in use through the 1930s at military installations across the British Empire. When American military planners start hunting for fast construction solutions in 1940, the Nissen hut seems like the obvious answer. The British have 2 decades of proven performance. The arch principle is sound. The structures work in combat zones. Why reinvent the wheel when you could simply license a working design and start producing them? But American engineers immediately spot problems that would make Nissen huts impractical for the scale and scope of the coming war. First issue: the British design uses specialized curved steel ribs that require custom manufacturing equipment. American steel mills are already operating at maximum capacity, producing armor plate for ships and tanks. Retooling factories to create uniquely shaped Nissen components would slow production of actual weapons. Every press stamping out hut ribs is a press not making critical war material. Second problem: weight. A standard Nissen hut weighs approximately 3 tons when disassembled. That might not sound catastrophic until you calculate shipping capacity. A Liberty cargo ship can carry roughly 10,000 tons, but volume matters as much as weight. The oddly shaped Nissen panels don't nest efficiently. You end up with wasted cargo space that could have held ammunition, medical supplies, or food. When you're island hopping across the Pacific, every cubic foot of shipping capacity becomes a strategic resource you cannot waste. Third challenge: the British design still requires semi-skilled labor. Those curved ribs need to be positioned precisely and bolted in a specific sequence. Get the angles wrong in the first few arches, and the entire structure will twist into an unusable shape. The bolting patterns aren't intuitive. British crews trained for weeks before they could assemble Nissen huts reliably, and even then, mistakes were common. America needs something a teenager with basic tool literacy can put together correctly, following simple illustrated instructions without extensive training. The final deal-breaker involves foundations. Nissen huts require carefully prepared concrete footings to anchor the steel ribs. Pouring concrete on a muddy Pacific island or frozen Alaskan tundra introduces all the delays the military is desperately trying to avoid. If the foundation settles unevenly, the entire arch structure can buckle and fail. The British got away with this in relatively stable French soil, but American forces need structures that can go up on coral atolls, volcanic rock, permafrost, and jungle mud without prepared foundations. So the Nissen hut becomes a starting point, not a solution. American engineers need to preserve the speed and simplicity of the arch concept while completely reimagining how such a structure could be manufactured, shipped, and assembled. The answer would come from an unlikely source, not from a military contractor with decades of experience, but from a construction company that had never built a military shelter in its entire existence. The George A. Fuller Company of New York had built some of America's most iconic structures: the Flatiron Building, the Lincoln Memorial, Pennsylvania Station. These were massive, permanent, prestigious projects that took years to complete. In April 1941, they receive a contract from the Navy that would transform them into one of the most important military suppliers of the war. The task: redesign the Nissen hut concept from scratch to meet American production and deployment requirements. The deadline: impossibly tight, because everyone with access to intelligence knows war is coming, even if Pearl Harbor hasn't happened yet. Otto Brandenburger leads the design team, and he understands immediately that incremental improvements won't work. He's the only licensed architect on staff at Fuller's Rhode Island operations, but his real qualification is different. He's a Swiss immigrant who served as a sergeant in the United States Army. He knows what soldiers need, what they can realistically assemble in the field, What will actually work under combat conditions versus what looks good on paper in an office. Brandenburger's team can't just make the Nissen hut slightly lighter or somewhat easier to assemble. They need to fundamentally rethink what a rapidly deployable shelter actually is. The team includes Peter de Jong, an engineer, along with Robert McDonnell, Tomasino Secondino, and Dominic Ergo, providing design and production support. This isn't a large team. This isn't a massive research department with unlimited resources. This is 5 men working under deadline pressure in Rhode Island, trying to solve a problem that will affect millions of soldiers. Brandenburger starts by asking a question. That sounds obvious in hindsight, but was revolutionary at the time. What if we designed this structure the way Ford designs a car? Ford's assembly line works because every component is identical and interchangeable. A worker doesn't need to measure, cut, or customize anything. Parts simply click together in a predetermined sequence. Could you apply that manufacturing philosophy to a building? Traditional construction says no, because every building site is different, every foundation is unique, and structures require constant adjustment as you go. A carpenter looks at the materials, makes judgments, compensates for variations. That's what makes construction a skilled trade. But Brandenburger's insight is that you could eliminate the site variability by making the structure itself so forgiving that precision foundations don't matter. Design the building to be more tolerant than the site conditions it encounters. Between April and June 1941, the team runs through dozens of prototypes. They test different steel gauges to find the optimal balance between strength and weight. They experiment with panel sizes. Too large, and they're unwieldy to handle. Too small, and assembly takes forever. They redesign every single connection point, because traditional bolts require wrenches, careful alignment, and time. What if connections used self-aligning tabs and slots that physically couldn't be assembled incorrectly? The breakthrough comes when Brandenburger's team stops thinking about walls and starts thinking about sections. Instead of individual steel sheets that need to overlap and seal, they create massive pre-formed arches that already include the curve. Each arch segment is a complete structural unit spanning 16 feet of width. You don't build the curve on site. It arrives at the construction location already shaped, already reinforced, already including the necessary corrugations for strength. But the real genius lives in the tolerance engineering. Brandenburger designs every joint with enough play that even if your foundation is off by 2 inches, the structure will still align perfectly. The arches have adjustable feet that can compensate for uneven ground. The side panels use a tongue and groove system that self-seals against weather while allowing significant lateral movement. You could assemble this building on ground that would make a traditional carpenter weep in frustration, and it would still be structurally sound. The team obsesses over fasteners. Every bolt, every screw, every connection point gets standardized. They reduce the entire structure to exactly 660 bolts of just 2 different sizes. An assembly crew needs only 2 wrenches to build an entire hut. Compare that to traditional construction, where you might need 30 different tools and hundreds of different fastener types, requiring constant sorting and selection. The psychological impact is enormous. Soldiers can memorize the assembly sequence in an afternoon because there are no special cases, no exceptions, no variations to remember. By late June 1941, Brandenburger's team has a working prototype that can be assembled by 8 untrained men in 36 hours. The Navy tests it brutally. They erect it in Rhode Island winter weather, then again in simulated tropical conditions with artificial rain and humidity. They deliberately assemble it wrong to see if mistakes are obvious and correctable. They drop panels from trucks to test durability during rough handling. The design passes every test. In August 1941, 4 months before Pearl Harbor makes war inevitable, the Navy approves full-scale production and gives it the name that would become iconic, the Quonset hut, named after Quonset Point Naval Air Station, where the first ones are deployed. The name comes from a Narragansett tribal word meaning long place. On July 18, 1941, the Navy officially adopts the name to distinguish their improved design from the British Nissen hut. The first Quonset huts arrive on August 23 aboard cargo ships that deliberately beach themselves to unload faster. Marines form human chains, passing crated components from the holds to the shore. Within hours, construction crews, many of whom have never seen a Quonset before, are assembling the first buildings. They work through the night using portable generators and work lights. By dawn on August 24th, Henderson Field has a functioning operations center, fuel storage, and an emergency medical station. 72 hours after the first components touch the beach, the base has 43 complete structures. Japanese bombers attack on August 25th and find a fully operational American airbase where empty jungle stood a week before. The pilots report back in confusion. How did the Americans build so fast? The answer is lying in crates on beaches across the Pacific, waiting to be assembled by men who've never held a wrench before this war. This becomes the pattern across the Pacific theater. Islands fall to American forces, and within days, Quonset cities rise from bare ground. Tarawa, November 1943. The battle ends on November 23rd, after some of the most brutal combat in Marine Corps history. By November 26th, just 3 days later, Seabees have erected a complete field hospital with 12 Quonset wards, surgical facilities, and recovery areas. The wounded from the next operation at Makin Island fly directly to Tarawa for treatment, instead of being evacuated thousands of miles to rear area hospitals. The Quonsets quite literally save lives by being exactly where they're needed when they're needed. Saipan shows the system at peak efficiency. The island is secured in July 1944, and within 10 days it hosts a complete B-29 superfortress base. These bombers are massive machines requiring specialized maintenance facilities. Traditional hangars would take months to build. Seabees connect multiple Quonsets end to end, creating structures 144 feet long with unobstructed interiors. A B-29 with its wings removed can fit entirely inside for major overhauls. By August, Saipan has 68 connected Quonsets serving as aircraft hangars, something that would have required months of construction and millions of board feet of lumber using traditional methods. The 3-day timeline becomes standard operating procedure, repeated so many times it stops seeming remarkable. Day 1. Site preparation and foundation work. Crews use bulldozers to level ground and lay wooden foundation beams. By nightfall, they have a grid of foundations ready for buildings. Day 2. Assembly. Multiple crews work simultaneously, each building a separate hut. The ribs go up in the morning, panels by afternoon, end walls by evening. Day 3. Finishing work and interior setup. Electrical lines, lighting, furniture, equipment, whatever the building's purpose requires. At sunset on Day 3, the building is operational and ready for use. The numbers from real operations prove the concept beyond any doubt. Tinian Island, summer 1944. 15,000 Seabees build 4 complete B-29 air bases in 37 days. Each base includes runways, taxiways, fuel systems, ammunition storage, maintenance facilities, housing, mess halls, command centers, and hospitals. Traditional construction estimates for equivalent facilities ran to 18 months minimum. The Quonsets make it possible in 5 weeks. By February 1945, B-29s flying from Tinian are bombing Tokyo, supported by infrastructure that literally didn't exist 6 months earlier. North Atlantic operations show the design works in opposite extremes. Iceland, winter, 1942. Seabees erect a complete naval air station in conditions where temperatures drop below zero and daylight lasts 4 hours. The Quonsets go up in snowstorms. Workers add double-layer insulation to the interiors and install oil-fired heaters. The buildings perform flawlessly at -20 degrees. Meanwhile, in the South Pacific, identical huts operate in 95-degree heat with 90% humidity. The same basic structure, adapted with different interior treatments, works from the Arctic Circle to the equator. Flexibility proves as valuable as speed. A Quonset erected as a supply warehouse in September converts to a repair shop in October and a barracks in November. As operational needs shift, Commanders realize they're not locked into permanent decisions. If the front moves and a base needs different facilities, they reconfigure what they have instead of building new. Some huts get disassembled, shipped to new locations, and reassembled. The logistics troops start calling them buildings with wheels, even though they never move on actual wheels. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Marines on Iwo Jima, in February 1945, experience the ultimate test. They secure the island on March 26 after brutal fighting that costs nearly 7,000 American lives. By March 29, 3 days after the battle ends, damaged B-29s are making emergency landings on Iwo Jima's airfields. By April 2, 7 days after the battle ends, the island has complete repair facilities, fuel storage, medical stations, and housing for support personnel. Over 200 Quonsets transform a devastated battlefield into a functioning forward base, while the ground still smells of cordite and blood. Every B-29 that lands there instead of ditching in the ocean represents lives saved by buildings that assembled in hours. The 3-day base isn't theoretical or propaganda. It's documented reality repeated dozens of times across 2 oceans. The Quonset hut makes the impossible routine. But here's what most people miss when they look at these curved steel buildings. The Quonset looks simple, almost crude. That simplicity hides engineering decisions that took months to perfect. Every curve, every dimension, every connection point represents a solution to problems most people never consider when they look at a building. Start with the arch itself. The semicircular shape isn't chosen for aesthetics or because it looks interesting. It's pure structural physics. When you place weight on an arch, the load converts to compression forces that travel down the curve and into the foundation. An arch doesn't bend under load the way a flat beam does. It squeezes, and materials like steel are incredibly strong under compression. This means the thin steel ribs, spaced 4 feet apart, can support enormous weight, despite being relatively lightweight. Snow loads that would collapse a flat roof simply compress the arch slightly, and the structure holds. Tests at Quonset Point prove that a standard hut can support over 40 pounds per square foot of roof load, enough for 3 feet of heavy wet snow. Pacific Island bases report Quonsets surviving typhoons that destroy traditional wooden buildings nearby. The curved surface deflects wind rather than catching it like a flat wall would. The spacing of those ribs demonstrates another calculation. Place them too far apart, and the corrugated panels spanning between them will flex and leak. Place them too close together, and you're adding unnecessary weight and cost without structural benefit. 4 feet represents the optimal balance. The corrugated panels are strong enough to span that distance without support in the middle. And the spacing means a standard 48-foot hut uses exactly 12 ribs. Everything works in multiples of 4 feet, simplifying manufacturing and allowing infinite expansion in 16-foot modules. Ventilation solves a problem that plagued the British Nissen huts and made them miserable to live in. Curved steel buildings naturally trap heat and moisture. In hot climates, they don't become ovens. In cold climates, condensation drips from the ceiling as warm interior air meets cold metal, creating a constant rain inside the building. Brandenburger addresses this with a simple but effective system. Each end wall has adjustable louvers near the peak. These create natural convection. Hot air rises and exits through the top, while cooler air enters through lower openings. The system requires no fans, no electricity, no maintenance whatsoever. Physics does the work automatically. In tropical Pacific bases, this passive ventilation keeps interior temperatures within 5 degrees of outside air temperature. Remarkable for a metal building under direct sun all day. The British Nissen huts could be 20 degrees hotter inside than outside, making them unbearable. Insulation adapts to any climate using the same structural framework. In Arctic installations, workers staple fiberglass batting between the ribs, then cover it with masonite panels. This creates a thermal barrier that maintains comfortable interior temperatures even at -30 outside. The military specifies different insulation depths for different climate zones: 2 inches in temperate areas, 4 inches in extreme cold, sometimes 6 inches in Arctic operations. The rib spacing accommodates all of these variations without changing the basic structure. A hut destined for Alaska looks identical from the outside to one shipping to the Solomon Islands, but the interiors are completely different. The corrugated panels serve multiple functions simultaneously. The corrugations add structural rigidity. Flat sheet metal would flex and buckle under wind loads, but the wave pattern creates a structure that's stiff in all directions. The galvanized coating protects against rust, critical in salt spray environments near oceans. The overlapping installation pattern means water can't penetrate seams. Rain hits a panel and runs down the corrugations to the next panel below, always moving outward, downward. Even in hurricane-force winds driving rain horizontally, properly installed panels remain watertight. The floor system is deliberately simple because it has to work on unprepared ground. The 4 foundation beams rest directly on leveled earth. Wooden floorboards span between the beams. This minimal foundation approach means a crew can set up on coral sand, volcanic rock, permafrost, or jungle mud without extensive site preparation. If ground frost heaves a beam slightly during winter, the building flexes rather than cracking. If tropical rains cause slight settling, the structure accommodates it. This flexibility would be a fatal flaw in a rigid masonry building, but it's a feature in the Quonset design. Interior adaptability comes from the clear span design, with no load-bearing walls or columns. The entire interior is open space that can be configured any way mission requirements demand. A hospital crew partitions the space with fabric curtains into wards. A repair unit leaves it completely open to work on large equipment. An administrative office installs temporary wall sections, creating individual workspaces. The same building houses 30 soldiers in bunks, or serves as a mess hall feeding 300, or stores 50 tons of ammunition. Some bases use oversized Quonsets 40 feet wide instead of 20, as vehicle maintenance bays, where jeeps and trucks enter through one end and exit through the other after repairs. The electrical and plumbing systems attach to the interior ribs using standardized mounting brackets. Conduit runs along the ribs, easily accessible for modifications. Lighting fixtures hang from the same points. This means a building can be completely rewired or replumbed without cutting into walls or ceilings. Combat damage from shrapnel or bullets is equally easy to repair. Unbolt the damaged panel, bolt in a replacement. Done. Bases keep spare panels in stock specifically for this purpose. A Quonset in the Philippines takes a seat. Direct hit from a mortar round in January 1945, destroying 2 panels and killing 3 men inside. The repair crew has the building fully functional again in 3 hours. The soldiers' bodies are carried out, the blood is washed away, replacement panels are bolted in, and the building goes back to housing troops that same night. All of this engineering sophistication disappears behind a facade that looks almost primitive. That's exactly the point. The sophistication lies in making complex solutions look simple, in designing a building so well thought out that untrained crews can assemble it perfectly without understanding the physics involved. The Quonset doesn't demand respect for its engineering. It just works, day after day, in conditions that would challenge far more expensive structures. June 6, 1944. The beaches of Normandy are chaos. Burning vehicles, wounded men, equipment scattered across the sand. Within 72 hours of D-Day, Quonset huts rise behind Utah and Omaha beaches, field hospitals treating casualties, command posts coordinating the advance inland, supply depots organizing the mountain of material pouring ashore. The structures that were designed for Pacific islands prove equally essential in France. By August, the Normandy beachhead hosts over 1,500 Quonset buildings, supporting 500,000 Allied troops. The huts follow the armies across Europe. As forces liberate towns and cities, medical units set up Quonsets to treat both military casualties and displaced civilians. In Belgium, during the winter of 1944, heated Quonsets serve as warming stations, where soldiers can recover from frostbite and exposure between frontline rotations during the Battle of the Bulge. In Germany, during the final push in 1945, they become temporary headquarters, prisoner processing centers, supply distribution points. Every function the military needs, the Quonset provides. Between D-Day and VE Day, over 30,000 units deploy to the European theatre. The Pacific theatre sees even more intensive use. By war's end in August 1945, American forces occupied dozens of islands, each one transformed into a forward operating base built primarily from Quonsets. The Philippines host entire cities of them. Hospitals, barracks, mess halls, recreation facilities, chapels, theatres, warehouses. Manila alone has over 3,000 Quonsets by liberation. Okinawa, secured in June 1945, becomes the primary staging area for the planned invasion of Japan. Within 2 months, the island sprouts massive infrastructure, airfields, port facilities, supply depots, hospitals, all built around Quonset architecture. When the atomic bombs end the war in August, Okinawa is ready to support an invasion force of 1 million men. Most of that readiness comes from buildings that didn't exist 10 weeks earlier. The final production numbers are staggering. Between 1941 and 1946, American factories manufacture approximately 170,000 Quonset huts in various sizes. The standard 20 by 48 model accounts for most production, but the military also orders 40-foot wide versions for hangars and warehouses, and smaller 16 by 36 models for specialized uses. The total covered area equals roughly 150 million square feet, enough to cover 3,400 acres, an area larger than many American cities. All of it prefabricated, all of it transportable, all of it assembled in days instead of months. The war ends in August 1945, and military planners assume the Quonset era ends with it. They're wrong. The buildings prove too useful, too economical, too practical to abandon. The production success creates an unexpected post-war problem. What do you do with 170,000 steel buildings when the war ends and you don't need them anymore? The military's first instinct is simple: sell them as surplus. The War Assets Administration announces that any citizen can purchase a complete Quonset hut for somewhere between $600 and $1,000, depending on size and condition, a fraction of what equivalent commercial building space would cost. Veterans get priority purchasing rights and additional discounts. Within months, advertisements appear in newspapers nationwide. Government surplus Quonsets available now, perfect for storage, workshops, or housing. American farmers see opportunity immediately. A standard 20 by 40-foot Quonset provides 800 square feet of weatherproof storage for approximately 1/10 the cost of building a traditional barn. Thousands of these structures migrate to Midwest farms, where they become equipment sheds, grain storage facilities, and livestock shelters. The curved roof means snow can't accumulate and collapse the structure during harsh winters, a serious advantage over traditional barn designs. The steel construction is fireproof, a massive benefit when storing hay or housing tractors with hot engines. Many of these farm Quonsets are still in use today, 80 years later, often with multiple coats of paint but structurally sound because properly maintained galvanized steel can last indefinitely. Small business owners buy them by the hundreds. Gas station operators use Quonsets as service bays. Rural mechanics convert them into auto repair shops, welding businesses, small manufacturing startups, equipment rental companies. Anyone who needs covered workspace but can't afford traditional commercial construction buys surplus Quonsets and has them trucked to their property. The housing applications get more creative and sometimes desperate. The post-war housing shortage is severe. Millions of veterans return home simultaneously, while wartime construction focused exclusively on military needs. Some veterans purchase Quonsets, add insulation to the interior, partition the space into rooms, and move their families in. These aren't luxurious homes, but they're weathertight, cheap, and available immediately when nothing else is. Communities of Quonset homes spring up near universities where the GI Bill creates sudden housing demand from returning soldiers pursuing education. The huts house students and their young families while they complete degrees. Churches discover Quonsets solve their expansion problems elegantly. A growing congregation that can't afford a traditional building addition can purchase a surplus Quonset, position it beside their existing structure, cut a connecting door, and instantly gain assembly space for a few $1,000s. The curved ceiling actually has decent acoustics for singing. Some congregations use them for decades before eventually replacing them with traditional construction once finances improve. Universities and colleges prove to be the best customers for surplus Quonsets. Michigan State College sets up 75 Quonset huts to house veterans studying under the GI Bill. Similar installations appear at campuses across the country. Some of these educational Quonsets remain standing decades later, repurposed as storage or specialty facilities. The design influences post-war architecture in subtler ways too. The success of prefabricated modular construction demonstrates that Americans will accept non-traditional building forms if they're functional and affordable. The mobile home industry borrows lessons from Quonset manufacturing. Standardized components, factory assembly, highway transportability. Modern pre-engineered metal buildings used for warehouses and retail stores descend directly from Quonset engineering principles. Self-supporting arches, bolt-together assembly, elimination of skilled labor requirements. Walk through any commercial area today and you'll see buildings whose design philosophy traces back to what Otto Brandenburger figured out in Rhode Island in 1941. Military and emergency response organizations never stop using the basic concept. When natural disasters strike today, relief organizations deploy modern descendants of the Quonset hut, tensioned fabric structures or updated steel arch buildings that assemble rapidly using the same principles Brandenburger's team pioneered. The United States military still uses updated versions for forward operating bases in Iraq and Afghanistan, calling them relocatable buildings or expeditionary structures, but using essentially the same curved steel architecture that worked in World War II. Perhaps the most unexpected legacy lives in Antarctica. Research stations at the South Pole and across the Antarctic continent use modified Quonset-style structures because the arch design handles snow loading brilliantly, and the prefabricated construction can be assembled during the brief summer months when ships can reach the continent. Scientists working at McMurdo Station or Amundsen Scott South Pole Station work inside buildings that trace their engineering lineage directly back to that Rhode Island design team working under deadline pressure in spring 1941. The numbers tell one story: 170,000 units, 3-day construction, bases built in 72 hours. But the real story is about solving impossible problems with elegant simplicity. The Navy needed to build faster than any military in history, in more locations, under worse conditions. Traditional methods couldn't meet that demand. They couldn't even come close. Otto Brandenburger looked at a British hut design from World War I and saw not just a shelter, but a complete reimagining of how buildings could be made. He understood that the factory, not the construction site, was where buildings should be built. He designed for mass production, for unskilled assembly, for universal application in any climate from Arctic to tropical. His team spent 60 days creating something that would save countless lives and help win the largest war in human history. The Quonset hut won the war, not in dramatic fashion, not in ways that make headlines or inspire monuments or appear in movies. It won by making the impossible routine. It won by turning months into days and skilled craftsmanship into simple assembly. It won by being exactly where it was needed, when it was needed, every single time. 80 years later, thousands of them still stand, rust-streaked and unglamorous, housing everything from antique cars to church youth groups to farm equipment to small businesses. They're not pretty. They were never meant to be. They were meant to work, and they do. That curved steel profile, that distinctive half-cylinder shape, represents something more important than architectural beauty. It represents the moment when American engineering stopped asking how to build better and started asking, what if we manufactured buildings like we manufacture everything else? The answer changed warfare, changed construction, changed how quickly human beings could create shelter anywhere on Earth. All because a Swiss immigrant architect and a small team in Rhode Island refused to accept that buildings had to be built the slow way, the traditional way, the way they'd always been built. Sometimes the most revolutionary ideas are the simplest ones. Sometimes changing the world just requires asking the right question and being willing to throw out every assumption about how things must be done. The Quonset hut looks like a simple curved shed, but inside that simple form lives a philosophy that transformed modern construction. Make every part identical, make assembly foolproof, make mistakes impossible, make the building forgive the site conditions instead of demanding perfect foundations, make it so anyone can build it anywhere. The civilian working with a wrench for the first time becomes as effective as the experienced carpenter, because the building teaches you how to assemble it as you go. That's the legacy. Not the steel panels or the curved ribs or the clever fastening system. The legacy is the idea that complexity can hide inside simplicity, that the most sophisticated solution often looks the most basic, and that sometimes winning a war requires rethinking everything you thought you knew about something as fundamental as shelter. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.